Hello, my name is Huntemann from the University of Bremen. Welcome to my poster presentation about the retrieval of thickness of thin sea ice from CIMR observations. This work was mainly done by Raoul Scarlett, and it is my pleasure to present it here. Passive microwave remote sensing has a long history in sea ice research. Many different methods were developed for different sea ice parameters, such as ice concentration, ice temperature, snow depth, multi-year ice fraction, or thin ice thickness. Studies showed that brightness, temperature, sensitivity of different parameters vary with frequency. Many methods rely on empirical relations such as fit functions or tie points of various brightness temperature channel combinations. Often this is done with respect to a single quantity, and any deviation is treated as noise. Also, this noise is often geophysical noise and has a relation to actual measurable quantities. The thickness of thin sea ice, for example, turned out to affect other retrievals such as ice concentration. The lower the frequency, the higher the effect of thin ice within a footprint. Higher frequency channels are more influenced by the atmosphere. Overall, it's a sort of interweave problem. This slide highlights our general setup with optimal estimation using AMSA2 and SMOS brightness temperatures. 14 channels are used in total, which are fed to this optimal estimation method, retrieving 8 parameters, where the thickness of first-year ice was added in this study. The method allows to put uncertainties to the brightness temperatures and also allows to put covariances to the geophysical parameters. Also, a priori knowledge can be fed into the method. Let's have a look at some first results. On the left are more atmospheric parameters or sea surface parameters, while on the right there are the ice parameters. So let's focus more on the ice parameters here. The ice surface temperature looks a bit patchy. At the ice edge you see higher temperatures, which are sort of realistic. However, in the Bering Strait there's also temperatures above the freezing point. The multi-year ice fraction shows a realistic image, just multi-year ice north of Greenland and in the central Arctic and at France Strait. The sea ice concentration looks quite realistic, and we compare it here directly to the University of Bremen ASI sea ice concentration product on the right. The only difference which we can see is mainly in the Bering Strait, where the ASI shows lower values than the optimal estimation. This is also the exact region where the ice surface temperature had unrealistic high values in the OEM output. Comparing the first-year ice thickness map with the University of Bremen's SMOS ice thickness product, you can see that the values are quite low, especially in the marginal ice zones, and also patchy in the center, where there's higher multi-year ice concentration, thus lower first-year ice fraction, which could influence the results of the retrieval here. One way of understanding the results and debugging the method is to look into the residuals, which is a difference between the forward-modeled brightness temperatures and the observed brightness temperatures. In this case, at 1.4 GHz, for example, we see quite some high differences at the thin ice areas, namely in the Baffin Bay, Bering Strait, and in the Barents Sea. The distinct patterns in the residual maps of 1.4 GHz could mean that the forward model needs some more improvements here. So as a summary, we combined AMSA2 and SMOS brightness temperatures as input for the optimal estimation method. We included a thickness relationship as parameterization for all frequencies using the round-robin thin ice data package into the forward model. First results show that the ice thickness has potential to improve the ice concentration retrieval in the OEM at freeze-up conditions. A couple of open issues remain. For example, the high residuals indicate flaws or hidden or missing parameters in the forward model. The empirical thin ice relation for all brightness temperatures is only based on the round-robin thin ice data package, which is only ranging from 5 to 30 centimeters of ice thickness. The collocation of AMSA2 and SMOS is quite problematic. SMOS 55-degree incidence angle observations are only acquired in forward-looking direction, and thus the source is relatively narrow. Also, there's a variable time difference between observations from both satellites, which is not too good for retrieving atmospheric parameters. Also, at the moment, only daily average brightness temperatures are used from both sensors. In future, CIMR and MWI from the METOP second generation platform will solve collocation issue from AMSA2 and SMOS while still having all frequencies. So possible use of physical radiation model for the sea ice surface component could improve the retrieval of ice parameters. With the radiation model, it would be also possible to test new parameters like snow depth or salinity. Thank you very much for attending our poster.